Hello and welcome back uh, to me answering questions from Robin Hartshorne's Algebraic Geometry. Today I'm going to be doing question 1.8 from section 1, so let's begin. This question asks us to show that the dimension of the intersection of an affine variety with a hypersurface not containing it has dimension 1 less than the dimension of the variety. Now we are going to use a couple of facts. The first is that the dimension of the affine coordinate ring of any variety is the same as the dimension of the variety. So let A of y be the affine coordinate ring of I, so k x1 dot 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 xn divided by the ideal generated by the elements of y. Now let z be an irreducible component of the intersection of y and h. Simple component of y intersect h. Now, by the third isomorphism theorem, we have the ideal generated by z over the ideal generated by I should actually qualify. The ideal generated by z contains that generated by y and that generated by h because z vanishes wherever y and h vanish wherever z vanishes. So I of z contains I of y and I of z contains I of h. Now the third isomorphism theorem is about two-sided ideals, but every ideal is two-sided in a commutative ring, and uh, as y is not a subset of h, I of h is not a subset of I of y. Now given this, I of z contains something which is not a subset of I of y, therefore I of z is not equal to I of y. Now the third isomorphism theorem, also I of z is a prime ideal, I of y is a prime ideal, etc. And let's call I of h f. So I of z over I of y is a prime ideal of uh, well, k da, 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 of over I of y, which is a of y. In fact, a of y over I of z, well, over I of y is isomorphic to a of z. This will be important later. So, as I of z contains the principal ideal generated by f, which is I of h, a hypersurface is defined to be the vanishing set of the vanishing set of an irreducible polynomial. Therefore, I of h equals f, just by definition, for some function f in our a of, well, for f in k from x1 dot xn. Now, as I of z contains f, I of z over I of y contains the ideal the principal ideal generated by the image of f in I of z. Now, suppose for a contradiction that suppose for a contradiction that our I of z over I of y would contain some prime ideal p containing f. Well then, if we unquotient it, I don't really know how to say that. If we unquotient it, then I of z would contain uh, some prime ideal q containing f. But that would violate the minimality of I of z within ideals which vanish on I of y and I of h, as z is an irreducible component. Uh, its 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 ideal generated by it is minimal, which is this is a contradiction. I still don't know the sign for contradiction. I know that it's two lines intersecting or three lines intersecting. Contradiction. Now, as f is not contained within our equals f, because of this fact, f is not contained within the ideal generated by y, uh, its generating element does not go to 0, so it is non-zero, and it is not, so f is not 0 as the ideal generated by its, well, its pre-image, I guess, um, as that is not contained in I of y. It is not a unit either, as plus I of y is a subset of I of z, which is not equal to our k x1 dot 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 xn, which I should say that this is because I of z, well, z is not everything. Oh no, z is non-empty. Z is non-empty. That's right. There. Now, this is the actual qualification for being a unit. It's an algebra fact. As Hartshorne does, I will just skip over algebra facts. Just like the third isomorphism theorem, I did kind of pull that out of a hat, but it is just a well-known algebra fact. So I will just say, hence, by Krull's I believe this is called the height theorem in English, but Holte-Delsatz is my best attempt. The oh goodness, the height of I of z over I of y equals 1, as it's a minimal prime ideal containing a principal ideal which is generated by an element which is non-zero and not a unit. Now, by theorem 1.8 from Hartshorne, we have the dimension of A of y over I of z over I of y plus the height of I of z over I of y equals the dimension of A of y. Or simplifying by one step, this is the dimension of A of z plus 1 equals r. And the dimension of the affine coordinate ring of a variety is the dimension of a variety. So, or of an algebraic set, the dimension of z equals r minus 1, which is what we wanted to prove. So, QED, that's what this box means, or it should be a square. But, thank you for watching. Smiley face. And I will see you again tomorrow.